Hello DSP guys, this is small note about lab 3. In this lab you are required to make some filter implementation and then group delay equalization. Okay, so when you make some filter, this filter have some phase response and accordingly some group delay response. And as we know from theory that if the phase is not a linear function, we'll have a group delay, and each frequency component of the wave will have different delay from the other frequency components, which will simply cause signal distortion. When I say signal distortion, then the sound is no longer the same sound, the signal is not the same signal anymore. So I'll say some hints about the procedure. The first point, design a third order Butterworth IR filter or any other filter structure. So I'll start the same way. So that's a Butterworth filter. This is third order. This is a low pass filter, cutoff normalized frequency 0.2, and let's use FV tool to see it. Okay, so this is magnitude here, and then this is a low pass filter, and it's have some phase response here. This phase response is not linear. Maybe it looks like it is linear, but if we get this line like this is not linear at all. This is not linear. So let's plot the group delay as well. That's it. So there is an increase here, then a peak, then decrease. So this filter will cause signal distortion a bit. If I want this group delay to be a good one with no distortion, then this group delay must be a constant here. So I must fill this gap here by something so that the group delay will be constant here. And if I want to extend the linearity region, I should extend here also. I add something here to make this constant. It is like just I want to fill this part and fill a part here so that I have a constant here. Then this degradation I don't care because it is outside the low pass of the low pass region of the low pass filter. Okay, so to fill this part we can use an all pass filter which has one pole and one zero, and to fill this pass we use another all pass filter which has two poles and two zeros. Okay, so the first filter, which is one pole one zero, which will fill the first part, is on the form z minus a over z minus 1 over a. You can prove easily that this filter magnitude response is always constant, whatever frequency you are using. Just replace z by e power j omega. This is constant, z e power j omega. Find the magnitude and phase responses. You'll find the magnitude response depends on a only. This is easy, you can do it. So let's say that I choose these parameters. 1, so this is z, the coefficient here is 1, and I suppose the a equal 2. So 1, negative 2. So here the numerator is 1 and negative half. Let's see the group delay now. Close this one. Okay, let's see the FEV tool. So the magnitude is constant as we predicted, and you can prove it easily. And let's see the group delay. This is the group delay as we want. So it is high. There is a peak here at 0, then it decrease, monotonic decreasing. So that's good. That's what we want. Okay. The second one here, the filter is on this form. Two poles, two zeros, z minus coefficient here a2 e power j phi, I called it p, this angle here, z minus a2 exponential e power negative p. So a2 e power angle, a2 e power negative of this angle. The zeros, the poles are the same, but instead of a it is 1 over a. So it's like cascading two of these, but instead of a only it is a e power j phi. You can also prove that this filter response is all pass filter. The magnitude is constant, whatever frequency you are using, and also it only changes the phase response. To find the B and A now, these are the numerator coefficients, these are the denominator coefficients. Z square, it is 1, Z, it is this multiplied by this multiplied by this, so it's these two terms. The constant term, it is A2, this term, A2, this term. You can find them here. The numerator is the same, but instead of A2 it is 1 over A2, and then we can calculate the group delay and the plot. So let's see here. So it's yes, so it is like the original one, but it is shifted. I have now two parameters, A2 and phi. These two parameters help me to select where is this peak and what is the height of this peak. So I have two parameters to move left and right and up and down. The first filter has only one parameter, which depends whether it's up or down for the peak which was here. This one has two parameters. Assume that I'm satisfied with these parameters. So what is the total group delay? It is just group delay 1, group delay 2, group delay 3. Group delay 1 of the original filter, group delay 2 of the first filter, which is 1 pole 1 0, group delay 3 of the 2 pole 2 0 all pass filters. This is the total group delay. The peak to peak here now it is like 1 and then decreasing. So actually the second filter is not good in this parameter. The first filter enhanced this part, but it's actually this is not the perfect one. If we left this figure and let's see the original one. So this is the original one. It's have been overwritten. Okay. Oh, it's have overwritten. Okay, no problem. Let's run it again. Okay, so this one it was like 3 and 4.5. This was 1.5 difference. This now is 1. Well, it's better, but this is not the best that I can do. So your problem now in the lab, you have three parameters. The first parameter is this constant A for the first filter, this constant for the second filter, this angle for the second filter. You have three parameters. You are trying to tune these parameters so that you have the total group delay as constant here as possible. You can just try changing the three parameters till you find the best combination, or you can think intelligently and find a way to figure what are the best of these three coefficients. And please don't come and ask me how to think intelligently. Either you find it or try with trial and errors till you find something good. If you finish and you have this plot, it's nearly constant, then you are done. Thank you.